projectile motion. So projectile motion describes an object that's launched from the ground or above the ground and falls back to the ground only due to the acceleration of gravity in a downwards direction. And that's only if we neglect air resistance, which in this case, that's exactly what we're going to do. And if it does neglect air resistance, it actually follows the path of a parabola. And here we're going to look at how we can describe the equation of the trajectory and the displacement, velocity, and acceleration in terms of vectors. So if it travels on the arcs of parabola, we're going to look at how our vector equations are going to describe each of these in terms of the displacement, the velocity, and the acceleration. So the vector equation to describe the displacement will actually follow the path of the trajectory of the object as it moves along the path. So the vector equation given a time t will tell us its displacement in terms of x and y as it moves along the path. For the velocity though, he will get an equation that describes its velocity that's tangential to the path on the curve. So the vector equation describes velocity will tell us this, and this will actually give us an x and y component every time for its velocity. The equation to describe acceleration will actually be pretty boring because acceleration is constant the whole time and it only acts in the y direction because that's we're neglecting air resistance. So acceleration due to gravity is just going to be the same as we move forward. So some things to note is that we're going to treat the acceleration in the y direction as minus 10 meters per second squared. Usually for gravity, or you could use minus 9.8 meters per second squared, or you can use minus g for gravity, either one of those. In the x direction, the acceleration of gravity is going to be 0 if there's no air resistance. Which means that we can establish a vector equation for acceleration being 0i minus gj. And if we just simplify that a little bit, we get acceleration vector being equal to minus gj. And that's actually our acceleration vector that'll describe what's happening to acceleration the whole time. So you can see it doesn't rely on time at all because acceleration is just constant for every point along its trajectory. Now, to get our vector equation for velocity, we need to integrate both sides of this equation with respect to time. Because hopefully you can remember that if we have displacement, which we call s, we can find the derivative with respect to time, and that gives us our velocity. And if we derive velocity, that gives us our acceleration. So which means going backwards, if we integrate with respect to time, this will give us our velocity, then our displacement. So that's exactly what we're going to do. We're going to integrate both sides here. So we're going to go the integral of a with respect to time and the integral of minus gj with respect to time. And the integral of our acceleration vector is just going to be velocity. And the integral of minus j is just minus, with respect to time, is just going to be minus gt j plus a constant vector. We could have added the constant on this side and then brought them together to make a new constant, but it's the same. That's the same result. Now to find that constant, we need to use some initial conditions. And to do that, let's imagine firing a projectile from the ground at an angle theta with a velocity v. Its magnitude, let's just call it v, our magnitude v, being the initial velocity. So let's let v equal the initial velocity. That's going to be our initial v, which means that our x component of the velocity will just be v cos theta, and our y component of the velocity will be v sine theta. And that's going to come in handy in a second. Because if we're launching this projectile with an initial velocity, that's the velocity when time is equal to 0. So we know that if time is equal to 0, our initial velocity vector is going to be the x component of that vector, v cos theta I, plus the y component, v sine theta j, at the beginning. So let's go ahead and sub those in. So we know when t is 0, our velocity vector is v cos theta I plus v sine theta j, and that's going to equal minus g times t, which we know is 0 at the beginning, times j plus our constant vector. This term is gone because it has a 0 multiplied by everything is 0, which means our constant vector is v cos theta I plus v sine theta j, which means that our final velocity vector is minus gt j plus v cos theta I plus v sine theta j. And just grouping our components together, it's going to give us v cos theta I plus v sine theta minus gt, all multiplied by j for our final velocity vector, where we can see in the x direction we have a component v cos theta and a y component of v sine theta minus gt. And from here we can go ahead and integrate both sides to get our displacement equation. So we're going to have the integral of velocity with respect to time being the integral of v cos theta I plus v sine theta minus gt j. And we're integrating all of that with respect to time as well. So integrating our velocity just gives us our displacement. Integrating this term with respect to time is just going to add it's going to be multiplied by a factor of t, because we can treat it like a constant because there's no t in there. Same with our next term. We're going to get v sine theta t. This term already has a t, so we're going to add 1 to the power and divide by the power, so we're going to get a half gt squared j plus our constant vector. And from that diagram before, we know that if we're launching the projectile at the beginning, its displacement is actually 0. So when t equals 0, its displacement is actually 0I plus 0j. So let's go ahead and sub that in to find our constant vector. So we have 0I plus 0j for our displacement. This is when time is 0. So we're going to have v cos theta times 0I plus v sine theta times 0 minus a half g 0 squared times 0 squared j plus c. That's all going to go because we have a 0 multiplication, so is that, and so is that. So all we're left with is 0i plus 0j equals 0i plus 0j plus c, which means that our constant vector has to be 0 in this case. And the only reason it wouldn't be 0 is if you actually launch the projectile from not the ground, somewhere higher. So you can see if we launched it from up here, it would have a y component that wasn't 0, and we could equate the coefficients here, and that'd be the only thing that would change it if it wasn't launched from the ground. So we can get our final equation for displacement being displacement vector equals v cos theta t times I plus v sine theta t minus a half g t squared, all multiplied by j. And this is our final equation to describe the displacement of something in projectile motion. From here we can get a few more formula that will help us describe what's happening in the projectile motion. One of those things is what is the maximum height that the object will reach. So in the path, the maximum height occurs up here. And if we think about it, we're constantly having a y component for velocity that's getting smaller and smaller and smaller until it's 0 and then starts increasing again as it falls back down. So at this maximum height, that's where the y component of the velocity is 0. So if we have a look at our velocity vector, that's v cos theta I plus v sine theta minus gt j. And the y component of the velocity is right here, and we need that to be 0 for the maximum height. So all we have to do is just say that v sine theta minus gt is equal to 0, and we make t the subject, so we can add gt to both sides, and we then divide both sides by g, so we get t is equal to v sine theta over g. And this will give us the time in which the maximum height occurs. And to get the maximum height, all we need to do is sub that into the y component of the displacement. So remember, our displacement equation, or our displacement vector, is vt cos theta I plus vt sine theta minus gt squared on 2j. And to get the maximum height, all we need to do is sub it into the y component of the displacement. So we have v outside of v sine v, so v times t, which we know is v sine theta on g, times sine theta minus g on 2 times t squared, which we know is v sine theta on g, all squared. And tidy this up a little bit, so we get v squared sine squared theta on g minus g on 2 times v squared sine squared theta over g squared. Here the g and one of those g's will cancel, so we get v squared sine squared theta on g minus v squared sine squared theta over 2g. We can now go ahead and just multiply both of these by 2, numerator and denominator, so we have the same denominator, and just subtract our numerators, and then 2v squared sine squared theta minus v squared sine squared theta is just going to give us v squared sine squared theta for our maximum height of the projectile. Let's have a look at the time of flight of the projectile. So we know when the projectile is launched, the time of flight occurs at the end. So we want to know how long it takes for it to get to there. And one thing we do know about this point here is that for the displacement vector, we know that at this point here, it doesn't matter what the I component is, but the Y component will be 0 at this point because it's on the x-axis. So let's go ahead and make the Y component of displacement 0. So the Y component of the displacement is just Vt sine theta minus gt squared on 2. This is all the part multiplied by j. And now we can actually factorize out a t. So we have v sine theta minus gt over 2 equaling 0, which means that t has to be 0, or v sine theta minus gt on 2 has to be 0. And it makes sense that t is equal to 0 because at the beginning it's also on the x-axis. So that's that solution there. And solving for t, so we can times everything by 2. So we get 2v sine theta minus gt equals 0. And now add gt to both sides. So we get gt equals 2v sine theta. And dividing by g is going to give us 2v sine theta over g for the time of flight. Now, we can also get the range of the object, so how far it's come across from where it was launched, by subbing in that time into the x component of the displacement. Let's go ahead and do that. So the x component of the displacement is just Vt cos theta. It's our x component of the displacement, which is going to give us the range. We know the time that it takes to get there is 2v sine theta over g. So we're going to multiply that by cos theta. That's just going to give us 2v squared sine theta cos theta all over g. And 2 sine theta cos theta, that actually equals sine of 2 theta. And we get a final range of v squared multiplied by sine 2 theta on g. So we're going to go ahead and look at an example now. And the example we're going to look at, try to do a little bit of research and look at an example relating to soccer. So what we've managed to look up is that we have a goal. We have the soccer goals that are 18 meters away from where you are with the ball. And to get the ball in the top corner of the post, it's roughly at about a height of 2.33 meters. And we need to know what angle to kick the ball at to get it in that top corner if we have an initial speed of 129 kilometers per hour we can kick the ball at. And what angle do we need to kick it there? So what we need to do here is we need to first change our kilometers per hour to meters per second, because you can see we've got meters and this is in kilometers per hour. So to change that, we can just times by 1,000 and divide by 3,600. So times by 1,000 will change to meters, and dividing by 3,600 will change to seconds. And if we do that, we get about 36 meters per second. Now, from here, we want to go ahead and create our projectile motion equations. Actually, before we do that, we might draw a little initial diagram of what's going on. So if we're kicking the ball with an initial speed of 100, or we're going to use 36, we're going to use 36 meters per second with an initial angle, we can say that the x component of the velocity is going to be 36 cos theta, and the y component of the velocity will be 36 sine theta. So this is just our little diagram for our initial speed when we kick the ball. So this is when t equals 0. So we're going to go ahead and start with our acceleration vector, and we know it equals, so we're also going to use gravity. We're also going to use gravity as minus 10 meters per second squared, just to make things a little bit easier. So we know that gravity is the only thing that's acting for acceleration. It only acts in the y direction, so we get our acceleration equation equals minus 10j. From here, we can go ahead and integrate both sides to get our velocity vector. So our velocity vector is going to be minus 10tj plus a constant. We know the initial velocity, so that's when t equals 0. So over here, we know our initial velocity is going to be the x component, 36 cos theta, I, plus 36 sine theta j. So let's go ahead and put that in. For our initial velocity, 36 cos theta, I, plus 36 sine theta j equals minus 10. So initial velocity means time is 0, where that whole term is going to be 0. And that means our constant vector is going to be 36 cos theta I plus 36 sine theta j, which means that our velocity vector is going to be minus 10 tj plus 36 cos theta I plus 36 sine theta j. And just tidying that up, bringing the i's and j's together, so we get 36 cos theta I plus 36 sine theta minus 10t j. Again, we can integrate both sides of this to get our displacement vector. So integrating our velocity is going to give us our displacement, and integrating each one of our terms in our velocity vector. So let's just write it above just so we can see. So it was 36 cos theta I plus 36 sine theta minus 10t j. So these are the things we're integrating. Now the integral of 36 cos theta with respect to time is 36 cos theta t I plus integral of 36 sine theta with respect to time is 36 sine theta t minus, well, we can add 1 to the power here because it already has a t, and divide by the power, so we're going to get minus 5t squared j plus our constant vector. And we saw before, when we launch off the ground, that constant vector goes to 0. So that's our final equation for our displacement. Now, we know we had the situation where we knew the goal was 18 meters away and we needed to get it at 2.33 meters high off the ground for our trajectory. So we want to know what happens when the displacement is 18I plus 2.33 j. What does our angle have to be? So we can go ahead and sub in our displacement vector for our displacement and then equate the coefficients. So we can say that 18 must have to equal to 36 cos theta t, and 2.33 has to equal to 36 sine theta t minus 5t squared. So all I've done there is equated the i's with the i's and the j's with the j's. So what we want to do from here is make t the subject in this first equation. So let's divide both sides by 36 cos theta. So we get t equals 18 over 36 cos theta, which actually just gives us 1 over 2 cos theta. And then we can go ahead and sub this into this equation for time here. So we're going to get 2.33 equals 36 sine theta times t, which we know is 1 over 2 cos theta, minus 5 times t squared, which is 1 over 2 cos theta, all squared. So we get 2.33 equals the 36 divided by 2 is going to be 18, and sine on cos is going to give us tan, minus, we're going to get 5 times 1 over 4 cos squared theta. So let's go ahead and just simplify that a little bit. So we're going to get 18 tan theta minus the 5 on 4 we can write as 1.25. And we're going to write 1 over cos squared as sec squared. Now we can go ahead and change sec squared in terms of tan squared. So we're going to get 2.33 equals 18 tan theta minus 1.25. Sec squared is 1 plus tan squared. So we're going to change that sec squared into 1 plus tan squared and then go ahead and expand the brackets. So we get 2.33 equals 18 tan theta minus 1.25 minus 1.25 tan squared theta. So let's add 1.25 to both sides. So we're going to get 3.58 equals 18 tan theta minus 1.25 tan squared theta. Let's just take everything to the left hand side. So we're going to get 1.25 tan squared theta minus 18 tan theta plus 3.58 equals 0. So you can see we're starting to form a quadratic equation in terms of tan. And we're going to go ahead and divide everything by 1.25. So we just get a monic quadratic. So 18 divided by 1.25 is going to give us 14.4 tan theta, and then 3.58 divided by 1.25 is going to be 2.864 equals 0. Now we have a quadratic equation in terms of tan, so we can say that tan theta is going to be minus b, so minus 14.4 plus or minus the square root of b squared, so minus 14.4 squared minus 4 times 1 times 2.864, so it's minus 4ac, all over 2a, which is just 2 because a is just 1. Plugging all that into the calculator is either going to give you 0.2 or 14.2. Taking the inverse tan of both of those is going to give us theta. So the inverse tan of 0.2 or the inverse tan of 14.2. One of those is going to get, this one's going to give you 11 degrees and this one as 86 degrees. And in the real world situation, an answer of 86 degrees is Seems pretty illogical. You don't want to kick the ball up at an 86-degree angle, and so the answer must be 11 degrees.